Hi, in this video, I'm going to go through the AQA A-level Chemistry paper. This is the 2019 paper, and this is paper 2, Organic and Physical Chemistry. I'll just do the first half of this paper in this video and the second half in a later one. Okay, so first question about amines. Give an equation for the preparation of 1,6-diaminohexane. Okay, so let's write that down. So you'd have CH2, you're going to have 6 of those hexane and an amino group on each end. Sorry, let's start off with the dibromo, and we're going to replace those bromines with NH2 groups. Nucleophilic substitution reaction. We're going to need ammonia for that. We're going to get the diaminohexane produced. Six carbon chain, H2. Now we've got to balance this, and the bromine, well, they're going to come off as Br minuses, and they're going to go with the NH4 plus ion, so that's going to be NH4Br. We're going to have 2 of those. So that means to balance that, we are going to need 4 ammonias. Okay, so in this here, the extra hydrogen comes off the hydrogen there, and the bromines come from the 2 bromines that's on the haloalkane. Okay. Complete the mechanism for the reaction of ammonia with 6-bromohexylamine. Okay. Now this is going to be a nucleophilic substitution reaction. Okay, we'll worry about this bit in a minute. We'll do this bit first. So the nucleophile is the ammonia, so we need to draw a lone pair on the nitrogen there, and the lone pair is going to go to this carbon here, which would have a partial negative positive charge, because okay, so that goes onto there. The bromine's leaving. Draw the product. The product is going to be let's count the right number of carbon atoms. So an NH2 on that end, and the NH2 still on that end. Now, suggest the structure of a cyclic secondary amine that can be formed as a byproduct. Well, what could happen in that reaction? I'll just rub this bit out here. Instead of this ammonia, that ammonia doesn't react. This the lone pair on the amine group could just as well, that could attack there, and then the bromine would drop off. If that was the case, you'd end up, we've still got 6, we've got 6 carbons in the ring, joined by and nitrogen. So let's draw that. So I've got got 6 carbons there, 1, 2, 3, 4, 5, and 6. The nitrogen is going to be there, joined on to number 6, and the nitrogen will have an H there. It's a secondary amine because the nitrogen is attached to 2 carbon atoms, number 1 and number 6. Okay. But diaminohexane can also be formed in a 2-stage from 1,4-dibromobutane. Now the butane there is the clue. That is hexane. We have increased the number of carbon atoms by 2, and that's whenever you increase the number of carbon atoms, suggests that maybe we'd use cyanide as a reagent, and that would cyanide react with the dibromobutane? It would do, because it's a nucleophile. So let's draw the what would happen is just draw this out. It does not part of the answer, but you're going to have that there. That's going to attack there. That's going to attack there. That's going to happen on both ends. Okay, that's going to, so let's do that. So you're going to end up with, what would we need as the reagent? We're going to form with the nitrile on both ends. So I'll draw that. That's going to happen on both ends. So we've got our 4 bromines there. And it's not part of the answer. This is just us working it out. Got hydrogens there, of course. And we have then got to reduce that into the final product. So we're going to have 6 carbons with an NH2 on each end. Right, now we can see there that that is a reduction because we've actually added quite a lot of extra hydrogens there. We've added hydrogens to the nitrogen, and we've added 2 extra hydrogens on the carbon there. Okay, where those green circles are. Right, don't need to draw any of that. We just need to suggest the reagent. So this is the first step. What we're going to need for that first step? Well, we're going to need potassium cyanide. It's a nucleophilic substitution reaction, and you've got to get the mark. So you must say that that's got to be dissolved in water and ethanol. Okay, in order for that to work. Now for this second step here, that's a reduction. Now there's two different ways of doing that. You can either use hydrogen gas and a nickel catalyst. That's one possibility. Or the other thing you could say is you could use lithium aluminium hydride. Now, whenever you say that, to get the mark, you've got to say that it's used in ether. Ether is the solvent there. It will reduce anything else. If you dissolve it in alcohol or water, it will reduce them. So it's got to be in ether. You've got to say that for the mark. And just to note there that a very similar reagent, but doesn't work. It's not quite strong enough reducing agent. You can't use sodium NaBH4, sodium borohydride. That won't work. It's not strong enough reducing agent. So the second step is a reduction with, okay, and there's the possibilities there. Right, base strength. Why is 3-amino pentane a stronger base than ammonia? Okay, so let's just draw out 3-amino pentane. Okay, now what you normally have to say in these, whenever you're talking about base strength, you have to say, why are both of these bases? It's because they're basic, because the lone pair on the nitrogen can accept protons. Why is it a better base? The reason why is because the lone pair on the amine here, the lone pair on the amine has higher electron density. And that's because alkyl groups have a slight tendency to release electrons. Okay, so for your 2 marks, that is all you need to say really, but you do need to mention the lone pair. A lot of people don't mention the lone pair because I think that's kind of understood, but usually that's in the mark scheme. I don't know whether it is in that one, I haven't checked, but it usually is mentioned in the mark scheme. You need to say about the lone pair accepting protons. Okay, so justify the statement there are no chiral centers in 3-amino pentane. This question here, well, I've drawn 3-amino pentane already, so save me drawing it again. Here we go. Now, in order for a chiral carbon, you need 4 different groups, okay, attached to the carbon atoms. And that obviously excludes that carbon because it's got 3 hydrogens, that one's got 3, that one because it's got 2 hydrogens, and that one's got 2 hydrogens. Let's look at the only possible candidate for being a chiral center is this green one here, but that's got an amine group. It's got a hydrogen attached, that's different, but it's got 2 ethyl groups, okay? So it doesn't have a chiral center. You can probably see that if it was 2-amino pentane, then it would have a chiral center because it wouldn't be symmetrical. and you would have 4 different groups. Okay. A student prepared cyclohexene by heating cyclohexanol with concentrated phosphoric acid, and you dehydrate it. Okay, so just it doesn't ask you to draw that, but you're going to get that cyclohexanol. You're going to remove the OH and the hydrogen from the carbon next door, and you're going to end up with cyclohexene. And that is a required practical, and that's probably why they're asking about it. Okay. Complete the diagram of the apparatus used to distill the cyclohexene for the reaction mixture at 83 degrees C. Okay, so here is this is the thing here. Now, what's obviously missing at the top here is you need some kind of stopper, and that stopper, let's put a stopper in, should also have a thermometer in it. Okay, to monitor the, that you want to boil off whatever comes at 83 degrees C. And of course, the other problem is that tube was not going to work. It needs to have a second tube around it to make it a condenser. So a Liebig condenser there. And you should label that. So you should label the stopper and the thermometer and label the Liebig condenser. You should also label in that the water goes in, the cold water goes in there to cool it, and H2O comes out there. The 2 marks. Okay, right. The distillate was shaken with saturated sodium chloride. Now the distillate is the cyclohexene, not the cyclohexanol. Okay, and this hexene was separated from the aqueous solution using the separating funnel. Now, why can you do that? Well, it's because we've got an aqueous solution of sodium chloride. Okay, that will not mix with this, with cyclohexene, because you mostly van der Waals forces with that. It's a non-polar compound, whereas water, of course, is polar. It's going to form hydrogen bonds. It will mix. It's 1 mark, so all you have to say is they are immiscible. There's 2 M's in immiscible. They're immiscible. Okay, and that's why you can separate them with a separating funnel. Don't forget separating funnels like that. A little tap on it, and you shake the stuff up in there. You're going to end up with 2 layers. In that case, the cyclohexene is going to be less dense, and this is going to be the aqueous layer, and you just run off the aqueous layer and throw it away. Okay, for 1 mark, I think all you need to say is they are immiscible. Maybe say because cyclohexene, van der Waals forces only, and water, hydrogen bonds. Right. Now, the cyclohexene separated were obtained as a cloudy liquid, and the student, okay, the reason why it's cloudy is because it's got a little bit of water still in it. Okay. And to get rid of that water, you've got to use a chemical drying agent, which is calcium chloride. How can you tell that it was dry? Well, it stops being cloudy, the cloudiness disappears, and it becomes clear. All the water having reacted with the calcium chloride. Right, now this is a percentage yield calculation, okay, for this reaction. So I've just drawn in the equation there. Okay, so it tells us how many grams of cyclohexanol we start off with, 14 grams. And we end up with that volume of cyclohexene, but they give us the density of that. So we're going to have to work out the mass of cyclohexene from that. We've got to calculate the percentage yield. Well, the important thing to realize is that 1 mole of the hexanol gives us 1 mole of the cyclohexene. Right, let's work out the moles of cyclohexanol we've got then at the start. Just write alcohol. Right, the moles of the alcohol is equal to the mass over the MR. We start off with 14.4 grams. The MR of the cyclohexanol is conveniently 100 exactly. So that's equal to 0.144 moles. Right, we have a 1-to-1 ratio reacting here. So that means we should give 100% yield, the number of moles of the alkene. should be the same. If 100% yield, 0.144. So let's work out the mass of the alkene if it's a 100% yield. I'll call that mass of alkene expected. That's equal to moles times by the MR. Of course, 0.144 multiplied by 82 is the MR of the cyclohexene, which gives us 11.8 grams. So that's our expected mass of cyclohexene. Let's see what mass of cyclohexene we actually get. Right now, how are we going to work that out? We know the volume of cyclohexene, and we know the density. So we should be able to work out the mass there. So let's do that. So mass of cyclohexene obtained, mass of the alkene is equal to the density, usually have that symbol rho, multiplied by the volume. Well, the density is 0.81 gram per centimeter cubed, and the volume in centimeters cubed was 4.15, which gives us 3.36 grams. Finally, the percentage yield then. Percentage yield is the actual mass over the expected mass multiplied by 100. Right, that gives us 3.36 over 11.8 times 100. That gives us 28.487%. Now we should work that out to 3 significant figures. I think it asked us in the question, or even if it didn't, well, everything else is to 3 significant figures. So to 3 sig figs, that is the answer. Do it in green here is 28.5% yield. Okay, now cyclohexene reacts with bromine. Okay, so this is going to be electrophilic addition. We have an induced dipole on this bromine molecule, and so no permanent dipole, obviously, because bromines both have the same electronegativity. So we're going to have a little delta positive on that bromine because it's getting close to the negative, or the negative charge in the double bond. Okay, so the first, we draw an arrow coming from the pi bond onto that bromine. Okay, and now let's draw the intermediate. Right, so we have broken the pi bond, that's gone. The bromine has stuck to one of those carbons. It doesn't matter which one because it's symmetrical. It could be that one or that one. Okay. Right, now this leaves this carbon here with a positive charge on it. That's a carbocation. The final step in the mechanism is for that bromine there, that comes off as a Br minus. You draw one of the lone pairs, and that lone pair then goes on to the carbon there with a positive charge on it to form the final product, which is 1,2-dibromo cyclohexane. Okay, so that's reasonably straightforward. Okay. Okay. Okay, now we've got to work out an empirical formula. Okay. All right. It gives us the percentage of carbon by mass. Okay, it's a hydrocarbon. It's non-branched. Sorry. Okay. It's a non-cyclic branch. Sorry, it is branched. Yeah. All right. So let's work out the empirical formula. So I'm going to say that if you had 100 grams of the compound, you'd have 88.2 grams of carbon, and the rest would be hydrogen. So that's 11.8 grams of hydrogen. we need to work out the number of moles of each of those. So the moles, which is equal to mass over the AR, the atomic mass. So the moles of carbon we've got is 88.2 over the atomic mass of carbon, which is 12. And the hydrogen is going to be 11.8 over 1. To work that out, that gives us 7.35 to 11.8. So we've got to simplify that ratio of carbon to hydrogen. We've got to simplify it by dividing by the smallest number, which is 7.35. So 7.35 divided by itself, of course, is 1. 11.8 divided by that is 1.605. Now we need to make that into a whole number. So what can we multiply it by to give us a whole number? Well, if we multiply it by 5, that will give us a whole number. It will give you 1 times 5 is obviously 5. 5 times 1.605 gives us more or less exactly, just slightly over 8, but it's about 8. So we can say, therefore, that the formula of the isoprene is C5H8. Now, we've got to draw, it's non-cyclic and it's branched. So we've got to have, we can't have 5 carbons in a row. I'll draw it skeletal. There's 4 in a row. The only place you can put a branch is on carbon number 2, put it there. Right, so now let's look at the carbon to hydrogen ratio there. Now, if that was saturated, the ratio would have to be N to 2N plus 2. So that would be 5, and that would be 12. Now, it's not 12, it's not 10, it is actually 8. So that means we've got 2 double bonds in that molecule. Now, you never really get 2 double bonds next to each other, so I'm going to put one there, which means you can't have one in that position there. That's not really possible. So the only other place you can put it is there. Okay. If incidentally, if I'd put it in there, that's exactly the same. In the red position, that'd be exactly the same thing. So that must be our structure of isoprene. Also, yeah, I forgot to mention, it did say the empirical formula was the same as the molecular formula. So the molecular formula is C5H8. It's not, for example, C10H16 or anything like that, which actually wouldn't be possible, but it's not a multiple of that because the empirical is the same as the molecular formula. Okay, so it carries on talking about polymers. The insides of the golf balls are made from a mixture of 3 other polymers. The repeating unit for one of these is shown. Draw the skeletal formula of the monomer. Now, how do these monomers, how do these things polymerize? Well, what happens is you get another one. I'll draw it next door to it here. So that would be like that. And then you'd have the, okay. How does that monomer form? Well, you have a double bond there, and you have a double bond there, and then you break the double bonds and you form the new bond there. So we can see here, let's get rid of that, that our monomer must be what I've drawn there on the left, but without these two trailing bits here. Okay, so I'll just draw it again. So you're going to have a double bond there. So there are 2 double bonds in that molecule. Okay. Right, give the UPAC name of the monomer. Okay, so we've got 4 carbons long. So it's but something, and it's butadiene. Okay, and we've got to say where the carbons are. That's carbon number 1, 2, 3, 4. So it's buta-1,3-diene. Oh, actually, as for the skeletal formula of the monomer, I haven't drawn the skeletal formula there, so I've got to draw the skeletal formula. So we've got 4 carbons, and we've got one double bond there, and we've got one double bond there. A second polymer in the mixture has a repeating unit with the structure shown there. Now, I'm just going to be careful here about thinking about EZ isomerism. Okay, now, yeah, that's fine. Okay, but we've got the second polymer there. Let's now draw the third polymer is a stereoisomer. Okay, and that is, and how does this, why does it arise? Well, we've got a double bond here, and there's no rotation around a double bond. And so that gives possibility of EZ isomers. So on this side, we've got the two high priority groups, the CH2 and the CH2 here. On the same side, there'll be the other isomer. Draw the structure of the repeating unit of the third polymer. Right, it's going to be the same as that. So we're going to swap those two round. So CH2, CH, double bond. This time I have the H up there, and this group down here. Okay, so draw the structure, we've done that, give the reason why it arises. There's no rotation around a double bond. Golf balls can be recovered from lakes and ponds. Why do they not biodegrade? It's because all the polymers are addition polymers. So that means you've only got carbon-carbon bonds, and they can't be broken because they are non-polar. They usually ask this question comparing it to condensation polymers. Of course, in a condensation polymer like a polyester, you do have you have got a polar bond there, and they can be broken by nucleophiles. Doesn't ask that though. All you have to say is because those carbon-carbon bonds can't be broken because they are non-polar. Right, P and Q react in solution at constant temperature. The initial rate of reaction was studied in 3 experiments, okay, by measuring the change. Okay, in concentration of, changing the concentration of P over the first 5 seconds. So look, we've got concentration P here, starts off at 1 times 10 to the minus 2, drops to that. It takes 5 seconds to draw that, for that to drop. And we've got to use this to complete this table. Okay, it's a bit of an unusual question, this, and people are a bit thrown by it because it's a bit unusual, even though it's pretty easy. Okay, so how did you work out the initial rate of reaction for experiment 1? Well, what did they do? They worked out the drop. So rate is going to be equal to the change in conc, delta conc, change in the concentration, divided by the change in the time. Okay, what's the change in the concentration for that one? It's 1 times 10 to the minus 2 minus 0.92 times 10 to the minus 2. And the time taken was, well, it was 5 seconds. If you evaluate that, you get this answer, 1.4 times 10 to the minus 1.6 times 10 to the minus 4. So let's do it for number 2. What's the rate? The rate is going to be, experiment 2 is going to be 2 times 10 to the minus 2 minus 1.84 times 10 to the minus 2. That number there, all divided by 5 seconds. And that gives us 3.2 times 10 to the minus 4 is the rate of reaction there, twice as fast. Do the same for, let's do this in blue, number 3. What's the drop in concentration? Well, 0.5 minus 0.34. It's mostly minus 0.34. Divided by the time taken, 5 seconds. That is equal to, again, the same, 3.2 times 10 to the minus 4. Okay. Right, and so rub this working out. Put the working out here. Put space. say that was pretty easy, but people were sort of a bit thrown by it because it's quite unusual. Determine the order of reaction with respect to P and with respect to Q. That's what we're going to do now. Work out the rate, the orders. Okay. So let's compare experiment 1, experiment 2. What happens to the rate? The rate multiplied by 2 there. What has happened? Well, as you go from 1 to 2, right, what can we say about the concentration of P? So P, the concentration of P, that's gone up by a factor of 2, hasn't it? Yeah. And what's happened to the concentration of Q? No change. So therefore, simply doubling P doubles the rate. So it must be first order with respect to P. Now we need to work out the order with respect to Q, which is going to be a little bit more difficult. Okay, so which ones are we going to, which two are we going to compare there? Right, we want one where we keep P the same and only keep P the same, but only change Q. Okay, so we'll just scroll this down a bit. Right, now they change P all the time. Okay, so that's not much use. Let's look at 1 and 3. Okay, let's compare 1 and 3. The easiest, choose between 1 and 3. What have they done there? Right, P concentration, that has that's halved. What's happened to the concentration of Q? Well, the concentration of Q has doubled. What's happened to the rate? Well, the rate has doubled. Look, it's gone from 1.6 to 3.2. Now, this is the tricky bit. Halving P should halve the rate. But the rate doesn't halve, it actually doubles. So that means whatever you've done with Q has made it quadruple. So we can say doubling the concentration of Q makes the rate go 4 times faster. So that means it's got to be second order with respect to Q. Okay, I'll just say that again because it's a bit complicated. Right, the rate actually only doubles, but we would expect the rate to halve because we've done to P. So whatever we're doing with Q must make it go 4 times faster, and we've doubled Q. So doubling Q makes it go 4 times faster. It's second order. 4.2, we've done that. Sorry, we've done the order. Right, now I've got another reaction between R and S. And we say second order with respect to R and second order with respect to S. So let's write down the rate equation there. We know that rate is going to be equal to the rate constant, concentration of R squared, concentration of S squared. Okay. Now in this question, they give us the initial rate. They give us the concentrations of R and the concentration of S, and we need to work out K. So let's rearrange to get K. K is going to be equal to R squared S squared over the rate. And we need the units. Let's work out the units first of all. Well, on the top line, we have got mole per decimeter cube. We've got 4 concentration terms. So that's going to be mole per decimeter cube to the power of 4. The rate of the reaction on the bottom here, well, that's got units of mole per decimeter cubed per second. Right, so we can cancel out that mole per decimeter cubed there, and that makes that to the power of 3 instead. So let's multiply that out. So that's going to be equal to mole cubed dm to the minus 9 divided by seconds. That second going to bring it up onto the top line, so it's going to be mole cubed dm to the minus 9 . Sorry, I've done this the wrong way around, haven't I? That expression is wrong. K is equal to rate over the concentrations there. So that expression is going to be the wrong way up. Let's do that. Sorry about this. So we're going to have mole per decimeter cubed on the top per second. That's the rate. We're going to have moles per decimeter cubed to the power of 4 on the bottom. That simplifies to second to the minus 1 over mole cubed dm to the minus 9. Bring it all onto the top line. Second to the minus 1, mole to the minus 3, dm to the plus 9. That's our units. Okay. Right, now let's put in the numbers to work out the value of K. So that's pretty straightforward. K, the rate they tell us is 1.2 times 10 to the minus 3 moles per decimeter cubed. Concentration of R was 1 times 10 to the minus 2. So we've got to square that. The concentration of S is 2.45 times 10 to the minus 2. Square that. Work all of that out, you get 1,991.67. And the units, of course, of this over here. Now, we should give it to 3 significant figures because all our data is given to 3 significant figures. So that to 3 significant figures becomes 20,000. And the units are per second mole to the minus 3 dm to the 9. Okay, now this question was removed from the, they didn't mark this because they said there was a typo, because can you see this, this here, that should be a divide by sign, which it's not quite clear. It's a divide by sign. It looks like a 1 or an I or something. So they discounted this question, but we'll do it anyway. Okay, so right, we are given everything in that equation except the value of A. We're given the value of K, the activation energy, the gas constant R, and the absolute temperature. Okay, so what we're going to do, I would suggest what we should really do is we've got to work out E, mathematical constant, to the power of minus EA over RT. We've got to work out that number, put it in. So what I would do first of all, I think we're going to work out the value of EA over RT. We have to be a bit careful there. Now, R is measured in joules per Kelvin per mole. So we need to convert our activation energy from kilojoules into joules. We must be using joules because R is given in joules. So that's 96,200. The temperature, because that's in kelvins, has got to be, well, 25 degrees C, that's 298. So it's going to be 8.31 times 298. Do that in a calculator and store it in there. You get a value of 38.84. And the next thing, I'm going to put that value into here. So I'll do that on the calculator. So I'll do e to the minus EA over RT. So you're going to press on your calculator Shift Ln. That gives you e to the power of x, yeah. So you do Shift Ln, so e to the minus 38.84, and that gives you 1.345 times 10 to the minus 17. Okay, we know that number now, so we need to put that into the Arrhenius equation up here, put those numbers in to work out what A is. So K, they tell us, is the rate constant, 3.46 times 10 to the minus 8, is equal to this number, 1.345 times 10 to the minus 17 multiplied by A. So A, we just divide that, rearrange. A is equal to 3.46 times 10 to the minus 8 divided by 1.345 times 10 to the minus 17. And that gives us a pretty big number. It gives us 2.57 times 10 to the 9. And what we're going to have to do there is think about the units, really. Now, the units, and they have asked this actually in the past, so I'll just explain. Well, we've got the Arrhenius equation is equal to K is equal to A EA over RT. Now, whenever you do anything like this, raise a number to the power of, that has no units. So that means A and K have got the same units as each other. And what were the units of K in this particular reaction? K can have different units, of course. In this reaction, it's seconds to the minus 1. So the units there for A are seconds to the minus 1. As I say, it didn't ask you for that in that question, but they have asked that before a couple of times. Okay, this question is about isomers. Give a reagent to distinguish 2-methyl-butanol. Let's draw that first of all. Okay, so we have got there's 2-methyl-butanol. And let's do 2-methyl-butanol. Now, hopefully, you'll be able to see that the second one, this is a tertiary alcohol, whereas this one is actually a primary alcohol. Now, you can't oxidize a tertiary alcohol with potassium dichromate. You can oxidize the primary. With potassium dichromate, and it's got to be acidified. And if you do that, this one you can't. If you do oxidize, you start off with orange dichromate, and you warm it up, and the dichromate will be reduced to green because it forms a Cr3 plus ion. Don't worry about what it is. So how can you distinguish them? You warm with acidified potassium dichromate, and this one, the 2-methyl-butanol, will go from orange to green. With this one, you'll get no visible change. It will remain orange. Right, NMR question, unusually with some bromines in it here. And we're just talking about the splitting, okay? Now, they've all got the formula C4H8Br. Now, just to C4H8Br, now Br is like a hydrogen, so that's like having C4H10. So in other words, this is a saturated molecule. You don't have to worry about any double bonds. Okay, compound A has got a singlet, a triplet, and a quartet. Right, so let's try 4 carbons in a row. We've only got 4, and there's no double bonds. Well, where should we put the bromines? Let's just try here. That's not going to work because you can see, look, you've got hydrogens here. That's going to give you too many peaks. It's going to give you 1. Those 3 are the same. Those 2 are the same. Those 2 hydrogens are the same. 1, 2. That's 3, 4. It's going to give us 4 peaks. So we can't do that. Okay. Now, before we go through every possible alternative, we've got a singlet in here. Now that means the carbon to which it is attached has got no other hydrogens on it. Okay, so the only way I can think of doing that is by having, if you had a CH3 there, that will give you a singlet. If we've got both of the bromines on that carbon, so I think that's what this one is, A. So just get rid of that there. Okay, so I think A is going to be, I'll put CH2, CH3. That's going to work because look, this one is going to be a singlet. Those hydrogens, that's a singlet because that carbon's got no hydrogens attached. It's a singlet. Those ones there, that's going to be a quartet because the one next door, which I'll do in yellow, that's got 3 hydrogens attached to it. So 3 plus 1 gives you a quartet. And those, they are going to be a triplet because the carbon next to them, this orange one, that's got 2 hydrogens, 2 plus, yes. Okay, so that is A. Now we've got to think what B is. B's only got 2 singlets. Now that's not many for 8 hydrogens. Okay, so my gut instinct tells me this is probably, B is probably branched. Okay, and the only branch you can have, of course, is when you've got 4 carbons is like that. Right. We've got to stick 2 bromines somewhere there, haven't we? So let's put them, put the bromines, let's put them here on that one. Let's see how that works out. So you got, that's going to be CH3, that's going to be CH3, it's going to be H, and that's going to be H. Now you should be able to see that that can't be the answer because they're the same. That will give you 1, that'll give you 2, that's going to give you 3 peaks, and we've only got 2 singlets. So we've got to move the bromine. So let's try moving that bromine. So the only thing we can really do is put it on. Let's try, not that many different possibilities. With these questions, it is quite often trial and error. Let's put a bromine on there and leave one of the bromines there. So now we've got, I think that works. Okay, so that, look, these, that will give you 1 peak. They're the same, and they're the same. They'll give you peak. Are they both singlets? Well, they are, because if you look at the carbon next door for these ones, well, that carbon hasn't got any hydrogens. And also that is the carbon next door to these 2 in the green, yeah? So that would be 2 singlets. So that is the answer. Okay. Okay, compounds C and D both have the molecular formula C6H3Br. Now let's do this, okay, and D has got, this is all about the carbon-13 spectrum. Let's see what this could be. It couldn't, right, it can't be many things. Bromine forms 1 bond in organic compounds, so that's like having C6H6. And of course, the only way you can get, there's a lot of unsaturation there. If it was saturated, it would be C6H14, and it's way lower than that. You've actually got 3 lots of double bonds, and it's cyclic. This is obviously a benzene ring. Okay, so C and D obviously both contain a benzene ring, and we replace 3 of the bromines. Okay, we replace 3 of the hydrogens with bromines. Right, C has got 2 peaks in its spectrum. Okay, so let's put the bromine, let's try alternate bromines, okay? Now, you can see there that these carbons, they're all the same as each other. And these are all different. Let's do it in blue. Blue ones, they're all different. So you've got 2 peaks there in the 13C. So that would be C, right? Now we know we can't have that. Let's just try one with 4 peaks now. How are we going to manage that? Right, okay, so we've got our benzene ring. Right, let's put 1 bromine there, 1 there, and 1 there. Now let's see how many peaks that will give us. Right, so that carbon is the same as that, that's 1. This one here is unique, that's 2. These 2 are the same as each other, and that's the same. So that should be yellow. That's no good because that is giving us 4 peaks, isn't it? That, oh no, that is right. That's fine. That's 4 peaks, so that's good. We've got the red ones, the blue, the green, the yellow. That will give us 4 peaks. So that is what D is. Let's just let's see the other possibility we could have had. A bromine there, 2 bromines next to each other, and then 1 sort of there. How many peaks does that give us? Well, they're the same as each other. Now, these 2 are not the same. Let's call that number 1. That one there is not the same as that because it's not symmetrical anymore. Actually 3. That one's different, and that one's different. That would give you 5 peaks, so that can't be either of them. So yeah, that is the answer for D. Right, infrared. Okay, and this is a pretty straightforward. I think it's 3 marks. You have to. They give you 3 compounds, E, F, and G, and you have to match them up with the spectra on the right there. Okay, now just to remind ourselves that we're not really worried. Anything above below 1500 is fingerprint region, so we're just going to ignore that always. Yeah. Can't say what those peaks are. Right, now let's look at E. E is you've got a carboxylic acid OH. Okay, it's carboxylic acid OH. Now, carboxylic acid OH are always very broad. Okay, and they are to the left of the alcohol one. Now this very broad peak here is extremely characteristic of that is definitely got to be the carboxylic acid. Even without looking at the numbers, it's the shape that gives it away. And hopefully you recognize that this one, which is similar but different, and it's got like this dip in it, that's this blue bit is an alcohol. It's not an alcohol OH. Yeah, so that's got an alcohol in it, not a carboxylic acid OH. Incidentally, that little squiggle there, that's the CH peak, or they all got CHs in them. You see the CH peak is up there in that one. In the carboxylic acid, the CH peak kind of gets swallowed up. So we've got the alcohol and the carboxylic acid, and the last one must be so it must be F, which is the ester. Just to double check, has it got what's this here? Well, that is due to the carbonyl and the ester, and of course the carboxylic acid has also got that carbonyl in its ester, and also this alcohol G, that's also got the carbonyl. So it's not very helpful in that in determining those spectra because they've all got the C double bond in them. So yeah, just to reiterate then, so that one is the alcohol, which is, sorry, that's the carboxylic acid, which is E. This one, which is the alcohol, which is G, and this one is the ester, which is F. Okay, isomers X and Y have that C5H8O. Gives the name for isomer X. Well, it's pentanone. It's a ketone, own. It's pentanone, there's 5 carbons, and it's cyclic, so it's cyclic pentanone. Right, now explain why isomers X and Y can be distinguished by comparing each of the following. This is a 6 marker, so let's think about one at a time. Right, first of all, the boiling points. Let's do that here. Now the boiling points, you're going to say that Y is an alcohol. So that has a possibility of H bonding. They're the strongest intermolecular forces. So it's going to have a higher boiling point. Whereas compare that to X, X is a ketone. There's no possibility of H bonds there because no hydrogen attached to oxygen, but there is a dipole in that molecule, that's delta positive, delta plus. So you will have permanent dipole-dipole interactions. Of course, they are not as strong as hydrogen bonds, so they're going to have a lower boiling point. Okay, that's all you need to say about the boiling point. I think probably 1 or 2 marks for that. Let's talk about the 13C spectra next. Okay, right. Now, before we think about chemical shifts, let's think about the numbers of peaks we're going to have. Okay, so actually, I think I've pasted it down here. It might be convenient. Let's do that. Let's do it here. Okay. Now let's think about the number of peaks. Well, this one is going to have one, quite a bit bigger. How many 13C peaks is going to have? It's going to have that one there. That's unique. These two are the same. That's going to give you 3 peaks. Okay. So let's see, can we distinguish alone by the number of peaks? I don't think we can. So how many different carbon environments have we got in this one? We've got 1 there, 2 there, and 3 there. So that will give you 3 peaks. So you can't just do it on number of peaks. You do need to look at the chemical shift data to be able to distinguish them. How could you distinguish them? Well, let's look at X. That has got a carbonyl carbon, which tend to give you pretty high, where's it gone? Esters or acids, it says here. It's just basically or ketones. Okay, that's going to give you a high ppm. Number 1, carbon number 1 there is going to give you high ppm in the region 160 to 180, and you won't see that in compound Y. You're not going to get anywhere near as high as that. But what I think it's probably worth mentioning a compound Y is what you've got is first of all, yeah, the alcohol one, the number 1 there. That's going to give you a fairly high peak. That's going to give you, if you look here, alcohols and between 50 and 90. So that's going to give you ppm 50 to 90. And even more distinctive, I think, are going to be these 2 peaks here, because they're very similar to each other. But well, sorry, 1 peak. They are the same as each other. Beg your pardon. But that is this one here. That's going to be in the region 90 to 150. So it would be a little bit tricky, but I think you could do it because there's a bit of overlap here. Not quite an overlap here, but very close. Look, that 160 to 180 is a bit close to that, isn't it? Really? Yeah. But this is going to give you isomer X is going to give you this high one there. Isomer Y is going to give you this pair of this one reasonably high, one slightly lower. Numbers 2 and 3 in this compound, they're going to give you they're going to be 5 to 40 ppm. They're going to be quite low. And here you'll only have 1, carbon number 2, which is a low ppm of 5 to 40. Okay, so that's all we need to say about the carbon 13. Now let's talk about the infrared. I think I'll just go back and well, actually I won't bother grabbing it. But how can we distinguish in terms of infrared? I'll draw those molecules again. So we've got that one has got the okay. Right, this one in infrared, you are going to get a peak due to that, the carbonyl group, which is about 1680 per centimeters. That's the peak there. That might be a little bit tricky to distinguish because here we've got a CC, which is, I'd say it's a bit tricky because that is very close. That's about 1660 or something like that. They do slightly overlap. Centimeters to the -1, sorry. Centimeters to the -1, they do overlap. If you've ever looked at a lot of these spectrum, you'll see there are different shapes. This is slightly broader and deeper. Whereas the alkene absorbance, even though it's in the same region, is it's sharper, less broad, but shallower. I don't think you're going to get any marks for that. We look at the mark scheme, but that is true. But what would definitely give the game away with the infrared is this OH. You get a characteristic OH alcohol absorption at about 3, whatever it is, 350. That would be very easy to spot the difference. It would be a little harder to distinguish those because they're quite similar. Okay. Now, I think that is as far as I'm going to go with that paper. And I'll do the second half in the next video.